Example 9.1 of the hull cement data is not on the website yet. It's in your notes for notes 11. I think you're the only one that didn't get it. The hard copy, so I went up and made some Xerox copies for the overhead, which we'll work with today instead of the computer. And we may be working this way for a while because the other computer is busted. Okay, so you might as well get used to it now. There's one section I would skip for the first reading of this chapter, and that's section 9.1.2. You could read it or read it quickly if you want. It's all the theory in abstract for the discussion of the full model and subset model for means and performance of what happens. Basically what happens is, the short of it is that if you have a full model, let's say, and capital K is the number of regressors in a full model. And then we're going to have, and then so selecting the subset regression model. And then I think in the hull cement data, then K is equal to 5. So let me just show the picture and sort of give you the overview of what's going on in the chapter before we actually do a lot of theory. Let me see if I can pull this all the way over on this side, get to the screen. And the screen is okay. Let me turn this thing on. I don't think I'm going to use it. Let's see. Okay. Let's have a look at the hull cement data. Okay. There it is. Why is the... Maybe you could help us with this, Shane, or someone else who knows cement. Why is the heat evolved in making cement with 4 ingredients, X1, X2, X3, and X4 of various proportions? And they're explained in the book a little bit. But I guess, isn't it true that when you mix cement, the heat comes out?
Yes.
Okay, that's what I thought. There was some question as to whether that was true last night or last time. Okay? So, and this is, for some reason they're interested in the heat. That's the dependent variable Y. And then there are the various constituents of possible cements you might make, and the heat's evolved. All right, that's the hull cement data right there. There are 13 observations, 4 regressors. So actually I think maybe I put the wrong thing for what's K. It's K, there's only 4 regressors in the full model. K equals 4 for the hull cement data. K equals 4. Okay. And maybe I'll lift it up just a little bit more since we don't need to look at the rest. Well, maybe just lift it up a little bit so I can get a little bit more room. And what's P? P equals the number of columns in the subset X matrix. Is the number of regressors in a subset model plus 1, all right, plus the intercept, all right? So P is 1 if there's only an intercept. Right? That's the standard business. The number of columns of the corresponding X matrix to model the regression. And if if you were going to do it by hand, right? And so you have the corresponding matrix X sub P equals corresponding corresponding design matrix for the subset model. So you have X sub P is the first column is the intercept. We're going to assume always an intercept in these models. And then you have X K1, XK2, whatever for, this is the case. Blah, 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 blah. This is for the case. P is equal to 3. You have 3 columns, right? 2 regressors. I just call them XK1, 1 regressor, a second regressor. Okay. That's simple enough?
What's CP?
CP? Oh, okay, yeah. We're going to get to that. Mallow's CP statistic. Okay? It's a statistic. All these things up here, what this is all possible regressions now. Suppose I just took all possible regressions. How many are there?
Possible linear regressions?
Yeah, we're just taking linear regressions. So we're only talking multiple linear regression, no higher order terms and so on and so forth here. Okay? Those can be obviously entertained in a polynomial model, what have you, but then, of course, this discussion subsumes that discussion in some sense. Because we're just looking at all possible subset models, all right, all possible terms in the model. So x4 might be x1 squared, if that's your, okay? That's possible. So these, when you see the products here, x2, x3, it does not mean x2 times x3. It just means that's what the model consists of, the subset. Instead of using curly brackets, they just concatenated the 2 symbols. So regressors x2 and x3 are in this model. Okay? And so there's the P, goes from 1 to 5. How many possible subset models are there then? Count them, right? 14641, 14641 adds up to 16, 2 to the 4th. The number of subsets, including the empty set, which means no regressors, of a set of 4 distinct objects. Here the 4 distinct objects are the 4 regressors, is 2 to the number of elements of the subset. So I'm the number of elements of the superset. Okay, 2 to the 4, 2 to the k, subset models. Including the trivial one. Okay, including the full model also, which may or may not be trivial. Okay, the point is that you had some property evaluation data. You had 9 regressors. That's a lot of subsets. So in general, this table is extremely difficult to make, because there's a lot of statistics, there's a huge amount of computation involved. I think I have a maple sheet to do this problem, and it's several pages long. And then you have to collate all the numbers at the end. Okay? So unfortunately, this is, I'm sure it's automatic in a big program like Statistical Analysis System. But we don't have that right now. Okay? So what do we have? We have what is SS res P and so on, RP squared. This is just the regressions, the residual sum of squares. We have P regressors. What's happening with that? That always must go down, because you're getting a better and better, well, it goes down if you order these columns, okay? I mean, order these sub-ranges. But it's got to be smallest of all possible cases at all regressors. The full model has the smallest SS res. Called the SS res of P, where P is the size of the subset model. Then this is a full model. Yeah, this is a full model right here. Okay, it has SS res P minimum. That's just by the fact that you just get a better fit by putting more regressors. You can put 200 regressors, just anything. The time of the day, how many radios you have at home, you name it. Okay, put just a bunch of unrelated regressors together, you can still get a smaller SS-res, okay? But presumably all those other regressors are just noise. And the point of this discussion is perhaps in a large number of regressors case, a lot of the regressors are just noise, okay? So what's a subset that works? Now, in general, what you're going to get is if you define beta, he calls beta star equals the full model, call X the full design matrix, X prime X inverse X prime, that's this one. That's the full model estimate of betas. Of the beta, and of course beta can be beta which is beta 0, beta 1, all the way up to beta sub capital K. Alright? That's what beta is. And he's putting a star on it instead of a hat. I don't know why he does it that way. Puts a star on that one. And then he puts, if you do the subset regression model, he calls that beta sub P hat equals XP prime XP inverse XP prime Y. Okay? That estimates the beta P for beta equals beta P beta R, where you divide beta into two pieces. R is the number of regressors that are removed. So what would this look like if I just took this example of the subset model X2, X3 over there? All right, so P is 3. Right? If I just took, if I take that the subset model is if X2, X3 is subset model for Hall cement data, then what is beta is going to be partitioned into, see, I'm going to have beta 0, beta 2, and beta 3. Those are going to be the coefficients in the subset model. And then I'm going to have beta 1 and beta 4 as my beta R. Okay? This is my beta P and my beta R. That's all we're saying here. It's kind of you're dividing beta into two sub-vectors. Okay? And it's just, that's the notation. It's simply notation. Okay? Obviously, P is 3 in this case. This is a 3 by 3 matrix in this case for P equal to 3. This is 3 by 3. This is 3 by n, and this is n by 1, and you get a 3 by 1 vector here. Okay? So that estimates. Now, in general, if you've got the full model is correct, we'll assume. All right? That really, so we assume that this is y equals x, n by capital K plus 1, right? Beta plus epsilon is the full model, and we assume that that holds. Okay, that you've put enough regressors in the world that it's actually valid, and you have the might as well assume equal variance is 2. Okay, okay. So our normality is we'll get there, right? But so what's happening is that this we already know the beta star is unbiased for beta there for. Okay, that we already had in the earlier chapter. That's unbiased. What about this one? Well, it shows in that section that I said to skip a little bit on first reading 9.1.2 that this is biased. And actually, you had a problem really early in the semester where you had to say, suppose the full model, 2 regressors, right? But you estimate
with only one.
You make this estimate, okay? All right, where P is equal to 2, so 1 regressor, all right? Using only the first 2 columns of X. Then show what the bias is. Well, now it's done in general here in this later page. So if you had looked ahead, you could have found the answer, okay, in section 9.1.2. All right, so we've done that problem in some sense, okay. And we'll go back and discuss the rest of that section 9.1.2 in an example form exactly in that situation of two regressors versus one regressor. Okay. But here we have this. So this is all possible regressions. RP squared is simply the coefficient of determination, SSR over SST. SST is constant, of course, because it's always the same SST. But an SSR has to go up the more regressors you put in. Okay. So you can see that if I went from X1 model only, the X1 model only, and then made a set that was bigger than that, so X1, X4, for example, if I went over to here, then X1, X4, X2, something like that. If I went from this to this to this, the SSRs have to increase. And so the RP squareds have to increase. Okay? 0.53, 0.97, and 0.98. And of course it goes up even a little bit higher here. Okay? A little bit, but not much. So if you look at that, if you look at R squared only, hey, what's the difference between this model and this model? You say, well, I don't need an extra regressor. Or at most 3 regressors just from this cursory inspection. Okay. And why did I pick that sequence? Well, we'll see. This is the adjusted R squared. We're going to have some theory around that, and the mean square for residual mean square. So I'm dividing that one. Now, SS res divided by P divided. Okay, SS res P divided by N minus P. So that the N minus P is not constant because the P is varying, right? You divide them by less and less as you get down here. Right? You're dividing this by less. So 73 is being divided by N minus 4. Maybe take an easier one. 50. What is N? N is 13. N minus 4 is 9. How about N minus 8? That's easier. That's 5. Okay. This one, this 75, okay, is being divided by N minus 5, which is 13 minus, N minus P, which is 13 minus 3, which is 10. Okay, so you get this number. 74.76 goes to 7.476. Okay. That's the easy one. Okay. Okay. And then, of course, it gets divided by something less at the next level. So then the 48 is not being divided by 10. It's being divided by 9. Gives you the 5.345. Okay? So you can read this table. 48 divided by 9 gives you the 5.345 and so on. Okay, what is a CP? We'll get to that in a minute. All right, that's Mallow CP. And it's what you're really trying to do is find a subset model with a small CP. So what we're looking at here is some possible candidates in terms of CP and being small. These kind of numbers in here. 5.5, you might say that's a bit big, but that's going to be coming in here. Okay. And then you have one more down here, 7. Okay. Anyway, those are the CPs we're going to be looking at. Study CP in a little bit, so that's the most interesting statistic you haven't seen yet. Okay? All possible regressions. Tons of calculation. Okay? All right. I wish we could make that table for every problem. All right. Now, what I want to go back is discuss some of the theory here and bring it in and calculate Mallow CP, and then try to go through Hall's cement data. Talk about forward regression and stepwise regression today. Okay. Where we're going to try to have a method for starting from, let's say, square one, no regressors at all, moving forward and trying to get a subset model that seems to be adequate. Sort of a search method. There are various search methods. Okay. So this one will be biased, but I keep telling you in little fits what the story is. This one will be now with the hat will be biased. That's kind of the bad thing about that hat with no extra notation. But the P here, I guess, helps. Okay, this one will be biased for beta sub P. In general, they actually show it biased for beta sub P. What actually is it? What is the bias? They actually show a formula for it. I'll show you the formula without going through all the formulas, the derivation, because you could do that, I'm convinced. I'll just show you the formula at the end, and they actually have a typo. It's E beta sub P hat is equal to beta sub P, the subvector, okay, plus A beta sub R. They call it B sub R, but it's a beta sub R. That was a typo. We're at page 293, where A is a so-called alias matrix, XP prime XP inverse. So this is the general solution to that problem I referred to a moment ago. XR, where XR is the last R columns. Well, the R columns of X corresponding to the PR decomposition of the X matrix. Remember, this P involves the intercept. Okay, and this R is just regressors removed, so P plus R really is K plus 1. Alright? And this makes sense because this is a P by N and this is an N by R. And then you have all this is a P by R matrix. P by R matrix, and then this is that's the alias matrix. So this is P by R here. This was R by 1, so you get a P by 1 in the end here. So that's a general formula for what the expectation of beta P hat is. And what will you get? You'll see that if the last columns of X are orthogonal to the first columns of X, then the bias is 0. You saw that if you noticed that in your problem, if the regressors were orthogonal, then you got that. So the bias could be 0, or if the beta R is 0, if really the subset model is the correct model, of course the bias is 0. But in general, there'll be bias if you take a subset model. Suppose you have, you've taken some regressors out. Maybe there was some small effects of those regressors. Okay? But you just took them out. That would introduce a bias. Maybe that's bad. On the other hand, it turns out in the same theory, it's going to reduce the variance. The variance will be reduced. The variance of the individual regression coefficients are going to be reduced. So, is that good? Yes, it is. It's going to make better precision. Even though there's a little bias, it'll be more precise. Each time you perform the experiment, you'll get around the same number. Okay? So there's smaller standard errors, but there's a bias. So how do you measure? How do you compare two estimators then? Is it good to maybe take a few? Maybe a little bit smaller subset model than you might ordinarily have? Perhaps, because you have to gauge basically how good an estimator is. What you do is talk about the mean square error of an estimator, theta hat. Okay, that's always defined to be the expectation of the square of the difference between just think of it as a real valued estimator. Don't think about vector value. Okay, so this is just a real valued estimator of some parameter, theta. If you take the expectation of the square, the difference between the two things. Theta hat is trying to be equal to theta, but it may actually be systematically biased, off even on average. But you calculate the expectation of the square of the difference. Okay, and that's equal by a little probability calculation to be we already know what the expectation is. It's always the expectation of the square. The square of the expectation plus the variance of theta hat. Variance of theta hat is the same as variance of theta hat minus theta. Okay? Remember, because theta is a constant, theta hat's not. So you get this, but this is called the bias squared plus the variance. So that's the formula for mean square error. And so if the bias isn't too big and the variance is smaller, that's a better estimator. So, in fact, in this later chapter on ridge regression, they actually use that strategy. They actually deliberately introduce some bias in order to get smaller variance. Okay? So, I don't know if we'll do that, but that's, yes, sir.
Alright, so when we've introduced this bias, is it asymptotically unbiased still, though? Like, does it still tend to be the right answer? Or does it tend to something that's shifted?
No, it's just bias. This is it. Here's the bias term right here. There's no n in here. This is just
that's right.
sitting there.
I get it now.
Okay. It's just a question of whether this is big compared with the variance savings. Okay? A, like I said, A may cancel out. All right, depending on whether the columns are orthogonal or not. Okay. So we'll look at an example. All right, we'll look at an example in a minute. Well, let me go back now after giving this little preview, and go back and do some beginning of the chapter. It's a little bit heavy going in chapter at the beginning. There's a lot of algebraic results. Okay, and then also this section 912 is very difficult to read after about this point. Okay. So we'll punt and go back to an example and leave the rest of it for another day, I think. So, where do we start? We want to start with looking at RP squared. We know that the coefficient of determination goes up, and the author has a picture of it, the coefficient of determination going up. There are lots of pictures in here. On page 296, it's just a curve going up, okay, as a function of p. Of course, it actually isn't a function only of p, it's actually a function of the subset. But if you think of an increasing subset, sequence of subsets, like x1, x1, x4, x1, x4, x2, or whatever, okay, then of course you'll get a curve that's increasing. There's a smooth curve. It's, okay, obviously, p is not a continuous variable either. All right? But that's very intuitive what they're saying there. So how far up is good? I mean, how high? What's an adequate R square? That's the question that Aitken addressed. In other words, if I'm going to take a subset model, what would be something that would be minimum R squared that I might consider? I said 0.98. Remember how I showed you 0.97, 0.98, and then 0.98? Well, are those? Is the 0.97 good enough? Well, since it's close to 0.98, you might think so. Okay. But what if it wasn't what if it was more like 0.90, 0.97, 0.98? Was the 0.90 good enough? All right. How would you determine whether an R square is sufficient? Okay. So to be considered as a subset model. So that's one measure, and they do a calculation on the bottom of page 304. If you want to look in your textbook, and I'm going to derive that statistic right now. Okay, so what you'll do is to see whether R squared is adequate or not. R squared sub p. Okay. Well, how do you actually test a hypothesis? What you're going to do is you consider the hypothesis H naught that, okay, R equals regressors removed. Number of regressors removed. So I'm going to consider that under the full model, H naught, that beta K1 equals beta K2 equals, and so on, equals beta KR equals to 0. In other words, I'm going to take those R regressors and I'm going to set them equal to 0. Take them out of the model. Then can I reject that hypothesis? In other words, or can I accept it? All right? Right? So then I get an F statistic accordingly, right? So I consider taking those R regressors out, so remove the R regressors, and I consider the F test. If F is bigger than a certain percentage point, then I say, no, that's probably not a good idea. Okay? But if my sum of squares in the numerator of the F is small enough, then it's basically just corresponding to the X, those regressors being noise, then I just say, okay, accept the null hypothesis. So I have to compute an F statistic, right? So F is equal to, under H naught, F naught is distributed as FR n minus capital K minus 1, because this is the number of degrees of freedom for sigma hat squared. For sigma hat squared full, right? There's capital K regressors, one intercept. So this is how many parameters that I had to estimate. K plus 1. Capital K plus 1 is the number of parameters I had to estimate, so I subtract that number of parameters from n to get the degrees of freedom for the full error sum of squares. I think sigma hat squared sub full was the 5.98. Okay? In our example. MS res full. Okay? So that's the number of degrees of freedom. Under the null hypothesis, the F statistic that I will get is distributed as FR n minus K minus 1. R parameter is being set to 0 here. Where, and that F naught, where F naught is equal to all this stuff. It's the SS res P minus SS res full. I'll just put it as capital K plus 1, okay, divided by R. That's the SSH, right? This is my SSH thingy, okay? Okay, all divided by my sigma hat squared full, but I'm going to write it as SS res, so K plus 1, because I'm going to do some algebra, divided by n minus K minus 1, and it's ugly, but not difficult algebra, okay? Because of all the notation is just plain ugly. Okay, so that can be rewritten, believe it or not. I think I won't go to the details on this. This is an exercise, algebra exercise. Take the definition of the coefficient of determination. What is it? It's you put it basically what you do is you divide everything by SST, right? I guess this is all that it amounts to. Divide everything by SST. And what is that? That's an R squared P. Alright? This is an R squared K plus 1. This is an R squared K plus 1. So, I think it comes down pretty easily as RK plus 1. Let's see. This is an R squared P. No, I'm sorry. R squared P is 1 minus this. So R squared P is 1 minus SS res P over SST. Okay, that's what it is. So because of the 1 minus, what I get is RK plus 1 squared minus RP squared over 1 minus RK plus 1 squared. You can see that. So that's all that's being done. Divide everything by SST and put in that definition, and you get this. Alright, so that's what the F statistic is in terms of the R squareds. Alright, so I can just look at the R squareds column and we can compute that thing. Alright, now, I needed maybe an R column, okay? In this case, n minus k minus 1 is your 8. This is my 13 minus 4 minus 1, that's 8 in the top here. Okay? Equals 8. Alright? And, alright. So R squared P is adequate alpha. R squared P is adequate alpha at a, let's say, 5% level. Okay, alpha is the traditional level, 5% or 10%, what have you. Okay? If F naught is less than or equal to F alpha, R n minus k minus 1. In other words, if I fail to reject this hypothesis, then RP squared is adequate. Okay? My subset model is adequate. Right? So if this is true. Now what's if this F naught is not too big, in other words. Alright? My SSH is not too big. Now, what I'm going to do is I'm going to take that condition, F naught less than or equal to that, and what does that come down to? That comes down to, this is a little hard to follow, and it's just a formula in the book, but let me just write it down anyway. Okay, you'll see from the example. So what does this come down to? That comes down to well, I didn't put very many details in here. This turns out to equivalent to RP squared greater than or equal to RK plus 1 squared times 1 plus D minus D. Alright. For D equal to R over N minus K minus 1 times F alpha R N minus K minus 1. Okay, let's see what that is. Okay.
So if RP squared is greater than that value,
then it's adequate. Yeah, so that's a minimum R squared. Now for D, but now D depends on the actual, this D depends on the actual subset removed, because it depends on R. Only through the R, of course, but also, so what I'm going to have is a minimum. What I'm going to do is I'm going to relax this a little bit. RK plus 1 squared is fixed. What does this actually come down to? This actually comes down to a different formula also. You can write it this way, or you can also write it as, yeah, that's the way I write it. Let me think about RK squared being 0.9 or something, and I have a D, and I have something like D is 2. Alright, so 0.9 times 3 minus 2 would be 2.7, minus 2 would be 0.7. Now suppose I increase D a little bit. Does that increase this quantity? Suppose I put D up to 4. Then I get 0.9 times 5 minus 4, which is 4.5, which is 0.5. Okay, when I increase D, it relaxes the R squared a little bit. Okay? Makes it easier to get in, be adequate. What I'm going to do is take the maximum possible D here for a fixed alpha by increasing R in both places to the maximum. Okay? To sort of make a little bit liberal, okay, adequacy condition. It just makes it easier so I can get something uniform. All right? So define D alpha, take R equals maximum. It turns out that this F percentage points increase and also this factor increases at capital K. All right? And then I'll get D alpha equals capital K over N minus K minus 1 times F alpha K N minus K minus 1. Let's see what that is for our example. So with capital K equal to 4, N minus K minus 1 equal to 8. I already mentioned that. I get that this is equal, and alpha equals 0.05. Let's see, take the traditional one. I get that D alpha is equal to 4 over 8 times 3.84 is my F alpha, okay, which equals to 1.92. So I'm going to take, then I have R, I'm going to put R naught squared, therefore, is equal to, this is going to be my minimal R squared, is going to be RK plus 1 squared times 1 plus 1.92 minus 1.92. is equal to, RK plus 1 squared was my 0.98238 times 2.92 minus 1.92, and I get a number, 0.948. So what I do want to do is I want to say, this is kind of a, it's kind of a cooked up criterion, but it's kind of nice. You just do what you best you can, and say this is a good applied math criterion. Say I should take an R squared that's bigger than 0.948. All right, I shouldn't take a subset model that has a 0.90. All right, so it's just one measure, and you're going to have multiple measures of how to select a model here.
So
okay?
In this case, like this is all from the the Hall-Cement data.
This is Hall-Cement data that I'm choosing the RK plus 1 squared from. So that was my highest R squared. with 4 regressors.
You look at it, and there's potentially 1, 2, 3, 4, 5 models, or 5 models other than the full model that meet that criterion.
Yeah.
All right.
Yeah. And I think if you roughly look at those are pretty similar to the ones that had the low CP.
Exactly. Yeah.
Okay. Okay. But some of them had a not so low CP with a high R, with an adequate R square. Okay.
Right.
So there was one of them that had the CP was 7 on there. Okay. And one of them had a, yeah. Then there was one that was close to an adequate R square that had a CP of 22. All right. So we definitely go away from that one. It looks like. All right. So let's continue. Let's talk a little bit about adjusted R square. Adjusted R square is usually good for comparing two. Comparing models. What does it have to do with? Well, okay, so this is consistent with another part of the story. The upshot is very easy to give. All right, the quick and dirty. And that is that if you actually look at a function of the mean square of the residual error, okay, mean square for residual error as a function of p, then typically what happens is the subset gets bigger, that gets smaller, because you're explaining more of the model. Okay, explaining more of the variation in y by putting more terms in. But then at some point, maybe it kind of reaches a minimum and starts to increase again, because p's gotten large, so the error sum of squares, even though it's getting smaller, the estimate for the mean square of residual error is getting bigger because you're just throwing in too much junk. You don't have enough degrees of freedom to estimate sigma squared. In other words, SS res isn't going down anymore, but n minus p is going, in the denominator, is going down. So that means the estimate is going up. Okay? So it kind of dips and then it comes back up. All right, so you want to catch it at the dip, at the bottom of the dip. Okay, how do you do that? Well, you're going to plot them all and do it, just by eye. But you just look in the table, okay, and sort of try to find a small MS res, okay. And it turns out that's equivalent to the large R squared adjusted. Okay, so it turns out that R square adjusted for p, which is equal to 1 minus n minus 1 over n minus p times SS res p over SST, SST being a constant, is maximized if and only if MS res of p is minimized. So actually the two columns give you the same information. You can just check that in those columns, in that all possible regressions picture. Just see that that is so. Okay. Not very difficult to see, I think. You just maximize. This is maximized if and only if this is minimized. Overall p. And, well, subsets, actually. Okay? Well, that looks pretty easy to figure out. Where MS res p is equal to SS res p over n minus p. Well, you can see that immediately because here it is. Here's MS res p, and the rest of this stuff is a constant. Okay, and there's a minus sign, so that's trivial. Okay? Are we agreed that that's a trivial result? Okay. All right. So that's that one. Let's see, there was one more little problem in here. Then there's the actual then it takes a bit of algebra to actually verify the following statement.
Which I don't know if is in here. Okay. There's another little statement in here, but I don't think the author makes it. I made some statement in my notes. I don't think I'm going to go into it now because it's going to be too complicated. All right, let's go on to the example and then the CP thing. Okay? Exercise 913. Okay, let's go through this star business. Suppose the full model is, and we're going to use unit. I'm going to change it just a little bit. I'm going to go ahead and use the unit length scaling. So the intercept is going to be taken away. The full model is yi equals beta 1 xi 1. So I don't have to think about intercepts and inverting matrices that have the first column, inverting x prime x where x has the first column of ones and all that business. So where x...
And to do that, you just do y equals yi minus y bar and x equals xi minus x bar, right?
Yeah.
Okay.
Divided by its square root of its variability are coded such that S11 equals S22 equals 1, where S11 is summation. Well, okay, so that means that what I do is I take xi1 goes to xi1 prime equal to xi1 minus x1 bar divided by the square root of s x1 x1. Okay? I'll put it this way so that won't be confusing. Summation xi1 minus x1 bar squared. Square root of the variability. That's unit length scaling. And I can put the 1 into a j here and you cover all cases simultaneously. Okay, if you want. All right. J goes from 1, 2 up to k. All right. Suppose you have that then. This sum was on I goes from 1 to n, and the j was the regressor index. All right. I know it's ugly with the j in there, but anyway, just make j equal to 1 if you don't believe me. Okay? Okay, j equal to 1. Okay. Now, trust that this is true. So that's unit length scaling. So I don't have an intercept in there. And now then, consider the subset model. yi equals beta 1 xi1 plus epsilon I. Okay? Again with the unit length scaling on page 114. That's where that is discussed. Okay? Then beta 1 hat star equals estimate of beta 1 under the full model. This is the full model. Okay. Just recapping the things we already talked about. And beta 1 hat is going to be the estimate under the subset model. Okay. What is the variance of beta 1 hat star? Let's calculate the. We know the beta 1 hat star is unbiased for beta 1. Because of the general theory we had. Say, how do you do that? E of beta hat star, the whole thing, that's a 2 by 1 vector, right? Equals E of x prime x inverse x prime y, where x is the design matrix with just 2 columns in this coded form, right? X is just the xi1 and xi2 columns, there's no intercept. All right, and that was because expectation commutes with this constant design matrix. You get EY, but EY was x beta. That's the model. So then these things just cancel. You just get beta back. All right. However, EY is x beta. EY is not x sub p beta. All right. Is that okay? It's not x sub 1 beta. Whereas beta 1 hat is equal to x1 prime x1 inverse x1 prime y. Okay? And so when I put in x beta here, then the things don't cancel. Right? So you get that bias term, and by partitioning we can actually show this. I'll just show it here. So then E beta 1 hat is equal to x1 prime x1 inverse. This is a 1 by 1 matrix. It's a scalar. Okay? In this case. Times x1 prime times the expectation of y now is x, but like x beta, but now that can be written as x1 beta 1 plus x2 beta 2, where x1 is the first column of x and x2 is the second column of x. That's how I can always write a matrix multiplication. I can always think of it as multiplication as an inner product way of x equals x1, the first column, and the second column, and beta is just 2 entries of beta 1 and beta 2. There's no intercept here. So, you know, I've concatenated this way and concatenated this way, and just multiplying x beta is just taking a linear combination like that. All right, that's the way matrix multiplication is defined. You have this, and then so then you get the cancellation here. So this is equal to beta 1 plus this alias matrix times beta 2. Okay. X1 prime is a sideways vector. It's long. It's 1 by n. Right? Then x2 is long, tall. N by 1. So you get this first column of x and the second column of x inner product times beta 2. Alright? So it's x1 dot x2. Okay? Count 2 columns of x times beta 2. Alright? Maybe I should put it this way, inner product of columns. So if those are orthogonal, you get 0 there. All right. So there's the bias. Okay. Now what is the variance, though? We also have formulas for the variance. That's the next part of the question. Calculate the variance. 913 says to suppose this, suppose that. Show that the variance of the full model estimate is sigma squared over 1 minus R12 squared. Okay, so what's the variance of this beta 1 star? I'm going to get the CP very easy. I got to get through this. Okay, so what's the? I better just finish this. Beta 1 star. This is sigma squared times x prime x inverse 1 1 now, the actual 1 1 entry, because there's no intercept. It really is the actual 1 1 entry of that. Okay, which is equal to
let's see, how do you do that? Sigma squared. What is the X prime X matrix? The X prime X matrix, because we got unit length scaling, is a what? What's the covariance matrix? I mean, what's the X prime X matrix when the variables have unit length scaling? I think we called it W prime W before. Some of you did it on your test to get the variance inflation factors. It's the correlation matrix. Correlation matrix is 1, 1, R1, 2, R1, 2, where R1, 2 is the correlation between X1 and X2. R1, 2 equals summation Xi1, Xi2 minus X1 bar, X2 bar over, well, that's what it is with the unit length scaling. In general, it's divided by the square root of S11 times the square root of S22. Okay, like that. So that's what it is. Those are correlations. And so then to the minus 1, and then I have to take the 1, 1 entry. So what is the inverse of that matrix? So that's quite simple. 1 over 1 minus R1, 2 squared. And then you reverse the diagonal elements, but they're the same as 1, and then you put minus signs on the off diagonal. And I take the 1, 1 entry of that. Of course, 1, 1 or 2, 2 entries are the same. So this is the variance of beta 1 hat star is therefore sigma squared over 1 minus R1, 2 squared. If I go to the variance of beta 1 hat, on the other hand, that's simply sigma squared times x1 prime x1 inverse. Okay, but that is a unit vector. Okay, x1 was assumed to be a unit vector, so that's just the inner product of unit vector with itself is 1, which is sigma squared times 1 over 1 equals sigma squared. So this has the smaller variance because R1 2 squared is less than 1. So this is a bigger number. If the correlation between x1 and x2 is high, this could be there's a big variance inflation. Okay? Factor, and that's what you have. The variance inflation factor times sigma squared versus sigma squared. Okay, so you can see there's a battle. You want to this is beta, in our case, this is beta 1 plus R1, 2, beta 2. So I already talked about this inner product. In the case of the unit length scaling, that is just R1, 2. So then I have this as a bias, and then the variance. So what's the mean square error? Mean square error of beta 1 hat star, which is the one that's unbiased, is 0 squared plus sigma squared over 1 minus R1, 2 squared. The MSE of beta 1 hat is the bias, which is R1, 2, beta 2, that's squared. Remember, I'm squaring the bias and then plus the variance, plus sigma squared. So this can be less than that. And then you can check to see when the two would be equal and come up with a little equation. Okay? That's the exercise. All right, what about the CP? What the heck is that?
Heat capacity. Right.
That's a different CP. Okay. So this is the end of the exercise. It's in the notes too if you want. But what I'm doing is I'm doing the formula bias squared. MSE is bias squared plus the variance. I hope you've kind of caught that idea today. That's how you judge the quality. To compare two estimators, you compare these two things. If they're unbiased estimators, you just compare variances. What's the CP? Well, what I want to do is what I'd like to do is minimize the mean square error, the total mean square error. So I'm going to define the total mean square error is expectation yi minus yi hat squared, the summation. All right, so I'm going to estimate yi hat by using the subset regression, right? So I could put the little p in here if you want, okay, to indicate that I'm really using the p subset to estimate
the ith response. The ith response. So the ith response is y. That's a fixed vector y. Just the heat evolved, right? This is an estimated heat evolved using the subset model at the ith observation. Okay. So I'm going to define that, and I would like to make that as small as possible. I'm going to have to cut to the chase here because we're running out of time.
Well, you could just pick it up next time.
Okay.
This is a good place. It's like we're about to start something. Or we can go for another.
Okay. Well, maybe I should do is show you that you develop CP here. So develop CP next time. I'll just do that. But I think what I wanted to show was a little bit, so you can read ahead a little bit. So let's have a look at these two slides and finish it off with the slides. Because probably go to the slides now rather than to the theory. It's probably better. Okay.
What page was that?
The CP stuff in the notes is my page 4. In his book, it's pages 299 and 300. Okay, shows you a little picture. He's basically coming up with another little statistic that tells me how to minimize roughly this thing. Okay? And what I want to do is look again at the Hall cement data. What have I done here? Okay, first I want to talk about forward and stepwise regression. I don't know how much I'll be able to do, but what you do, making a lot of noise. Okay, is you have to first enter a first regressor. Let's start from square zero. You enter a first regressor into the model. Which one would you choose out of x1 through x4? Well, the one with the highest correlation with y. You can't see it here, but I've bolded this one right here. The correlation, I've taken not only the correlation between the x's, but also the correlation with y. So I can get, all I'm interested in is this first column here, actually. In some sense. I might be interested in the rest of the column to see if there's multicollinearity in the model. Which there is some, okay. x2 and x4 are very closely correlated, okay? But the correlation of the individual regressors with y, R1y, R2y, R3y, R4y, is our notation for them, are those. And so you have the highest correlation between x2 and y and between x4 and y, and x4 wins. So in the forward selection model, I put x4 in the model first. Okay, so then I do simple linear regression of y on x4. Okay, and I believe that is done somewhere. I don't know where it was done. Oh, it was done on the next page. I just stuck it over on the side. Okay. So on page 2, you've got these last pages in your notes. So here was the simple linear regression of y on x4. And I needed that as my base point, okay? And I got my SS res with what p is equal to 2 here, right? My one regressor, okay? And I've got my SS res is 883.9. Let's see if that actually fits that other little table I had in here. Yeah, there it was, and it was the smallest SS res, which is what I wanted. See, that's what I wanted. Among the single regressor models, 883, the smallest SS res, the largest the largest regression sum of squares, and most variability accounted for. The largest RP squared, 0.67 versus 0.66 for the variable 2. So lots of ways you can do them all, but instead of doing all those subsets, instead of doing 5 or 4 regressions, I just looked at the correlation matrix.
that's going to give the information. Because in fact, this RP squared is the square of the correlation, that 0.82 business. Okay. So I don't have to do all possible regressions is what I'm saying. All right. Now, how do I go to the next step? Suppose I want to get into which one of these 6 models should I go to next in a forward regression? There has to be some criteria. The criterion is, well, now you have to start doing something. Now what are the possible things? Well, obviously there's only 3 that I have to consider because I'm going to keep x4 in the model in this routine. Okay, so x4 and x1, x4 and x2, or x4 and x3. So which one should it be? Well, from 3 regressions where x4 and the 1 regressor is added, we find the highest t-statistic for the regressor after x4 is 10.4031. Here it is. That's the highest t-statistic among these 3 t-statistics. You had a 10, a 0.4, and a 6. Okay? So 10 is best. So then, in other words, x1 is the most significant among the 3 that I might have added. That's equivalent to the criterion that he mentions in the book, by the way, which is kind of, he goes back to correlations again. All right, but he has to do partial correlations. So you have to take the residuals after fitting for x4, y after x4, take the residuals, also take x4 after the other regressors take residuals, and take the correlation between those. That's complicated. I don't want to do all that. I still have to do 3 regressions, x4 and all the other regressors, then now instead of y and all the other regressors. But anyways, it's too complicated, so this is much easier to understand. I have to do 3 regressions here, and I find out which one is the highest. So now I'm going to take the model x4, x1. And then, this is forward selection, by the way. And then what happens then is, and also, what if the highest t was only 1.5? Do I take it? Or do I stop? Well, it has to do with Fn. Fn is the F statistic, the level at which you're going to go in. You're going to allow it to come in. If Fn is 5, then 1.5 squared is not big enough. All right, because the t squared is to f. Okay, so if I take Fn to be 2, yeah, it is big enough. Okay, so how easy am I going to let terms into the model? That's the parameter you set up in this game. This is a game, all right? So now I have x1 and x4, and I have to add another term. Well, there's only 2 possibilities now, all right? x1, x4, and x2, or x4, x1, and x3. And again, I look for the higher of the 2 t-statistics for the added variable. Okay? And so I get 2.24 and a 2. So the 2.24 wins. So I get x4, x1, and x2. Okay? Okay, and then if I go again, I think x2 after all those things is not that great. You can see how much error sum of squares is accounted for now. What's the error sum of squares in this model here? It's 47.97. The full model error sum of squares is just a tad smaller than that, right? It has to be smaller. The error sum of squares in the total model is 47.86. So am I going to add the last regressor? No way. It's not any improvement. Okay, you can see that by various criteria, but just from the F statistic alone, you can see I'm not going to do it. Okay?
So now you're looking at x1, x4, and
x2.
If you go, well, no, I was just saying, if you go back to the table where you do the one that looks like it's a better model is x1, x2.
Okay, let's have a look. Yeah, but here's another situation, though. Suppose I have x4, x1, x2 now. Now, before I had x1, x4, right? Okay. And x4 was still significant in x1, x4. Okay? So I kept it. What if it hadn't been significant? Could I throw it out and go back to just x1? Yeah, of course, then that wouldn't have been the case because going back to x1 is a lousy thing. But now they got x1, x4, and x2 in it. What's the regression look like? Now x4 is insignificant. So in stepwise regression, I bump back to x1, x2, assuming that f out is big enough so that 1.3 squared is not bigger than f out. All right? 1.36 squared less than f out. In other words, do I keep a regressor or not? It's a simple idea, right? If it's less than f out, then I throw it out. Okay, so now I'm back to x1, x2. Okay, and now for stepwise regression with f in equal 5 and f out equals 3, we do not drop a regressor at the first two forward steps because 12.5 squared is bigger than f out equals 3. However, after the next step, since 2.24 squared is bigger than f in, we add it in. Okay, 2.24 squared is like 6 and some more. So we add the regressor in, but the negative 1.365 squared is less than 3, so we take that one out. So we put x2 in and take x4 out. If we now try adding x3, we are done because it's shown below the statistics 1.354 squared does not exceed f n equals 5. Thus, the best model has x1 and x2 by stepwise regression. So I got to x1, x4, x2 by forward selection. I got just to x1, x2 by stepwise regression. And the author, by arguing some more, looks at, just by simplicity case, looks at the fewer regressors has the minimum CP, and so on. He picks that as his best model. Okay. We'll discuss CP next time. And I don't know if I'm going to give you a pre-test or some kind of pre-test. We're actually going to have a final exam in class 2 weeks from Monday. I'm going to give you some kind of preview test to base the test on. Depending on how the results of this thing went, I might kind of use this type of model.